Maybe not.
Yeah.
Alrighty, here we are again for another programming tutorial with 5202. I'm your host, Samuel Flickinger. Let's get started. So, so, sorry, we go back. So starting out, so there are different types of there are segments in a match, I should say. There we go. That's better. So there are segments in a match. So there's autonomous and there's teleop. So autonomous is that first 30 seconds of an FTC match. Actions during the segment are all pre-programmed. And then teleop is the last 2 minutes of a match with drivers controlling the bot via the gamepad. So that's what we just learned how to program. We just learned how to program, how to hook up servos to buttons and motors to toggles, which is great. It's awesome. Okay. But why is this change important? Okay, why is this difference important? Well, that change in flow results in a change of code. So we go back to the op mode versus the linear op mode. So what we've been working with, this structure right here, this op mode structure. So we start out and we have our two methods. We have our init and our loop, and they run through respectively. You do this one once, and then you're going to loop this one over and over. But in a linear op mode, you're going to start out and you only have one method that you're running through, and you're running straight through that. And basically the only thing that you have in between, the way you set up, you have this wait for start command in here. What this does is this actually acts as kind of a separator between your initialization and your actual running. So this is kind of like the split up here. Like this is split up into two different methods, but this thing, it's the same thing since they both just run straight through. So they just have the separator as a wait for start right here. So we're going to go, now we're going to create an auto program. I'm going to go back into Android Studio, open up, we're going to create a new program over here. I'm just going to name it, I'm going to go back, we'll say first auto. Great. Go in, you can see it's already set up. Now, this time what we're going to do is change it so it's a linear op mode. Since we want autonomous programs generally are linear op modes because they run straight through, just like the structure. So the linear op mode matches up with the autonomous mode. And then teleop is more favored because teleop is more favored for op modes, regular op modes, because you have parts where you want to keep updating things, you want to keep checking your joysticks, you want to keep updating your motor powers over and over and over again. It's kind of repetitive. So that's where using that op mode with a loop really helps you out. Okay, so we're going to go in. So now we need to do this. We extend linear op mode this time. Linear op mode. I can't spell. Not linear gradient. Linear op mode. Okay, going to do this. It's going to ask me if I want that. I'll enter. Yes, I do. Okay, so I got to pop up. Now we set up this structure on the inside. So instead of our public void init, public void loop, we're going to do run op mode. And then over here after that, before we do curly brackets, we have to do this throws interrupted exception. Interrupted exception. This is just here so it can handle a certain type of error that's thrown its way. It's specific for this one, and I'm not going to get into that right now, but it's just there. It needs to be there. Okay, so let's go back and start working. Let's actually develop an auto program now. Now that we have the structure, let's start out. So we're going to get in. We're going to start working with encoders. So encoders are sensors attached to the motors that are used to track distance. So Andy Mark Never Rest motors have built-in encoders. Those are with the motors. But the Tetrix motors do not. So you'll have to install those, and those kind of come with the kit. Personally, I would recommend the Neverest motors for anything where you're tracking distance because, one, they're not only built in, but two, they burn out in 2 minutes and 30 seconds compared to Tetrix's 7 seconds. Not to say that there aren't uses for the Tetrix motor, but for your drivetrain, I recommend that for sure. Anyway, sorry for that deviation. But we can use those encoders that we have on the drive motors to move specific distances. That is supposed to be deep, but okay, here we go. So an illustration with Sambot right here. Go in, let's label a few things first. So we'll say that this point that we start at, this is our starting distance. We have this delta x right here. This is the distance we want to travel, and then this is the target relative to our starting position. And that's That's this endpoint right here. So now we're going to work through the relations between those identities that we worked with. So we have, if you notice, you take our target distance minus our starting distance, we get that delta d or delta x or whatever you want to say, that distance in between right there, that kind of the difference between those. So by knowing that starting position and then a distance we want to travel, we can determine the target position that the encoders need to reach. Now, another thing that we're going to find to be useful is that to get our current position relative to our starting position, we take that current encoder reading minus the starting position that we're at. Now, the reason why this may be like, oh, this is a little redundant, why the heck are we doing this? Why can't we just use that current encoder reading? And that's a great question. The answer to that is that if these values are, let's say, these don't necessarily start out at 0. So your current encoder reading, whenever you start out, it may not start at exactly 0. It may be like, it could be 0. It could be, but it's more likely to be something, just some massive number, or maybe a smaller number, but it's not going to start at exact 0. So you kind of have to offset that, and you fix it, and you put it back, and then you just kind of have this current position that you can reference off of, right? And then we use that to track our current movement, okay? So go through. So quick deviation. Let's go into loops just as a concept really quickly. So we saw a loop, but it was like a method of a loop. It wasn't a true one. So this right here is an actual loop. This is something that we can run through. So what happens, this is a structure of a basic one. We say while something is true, do this. So this is called a while loop. So then this keeps going until while this thing is true. And then whenever that thing is not true anymore, then it stops, okay? So the way that we use this with the encoders is we set it up. We can set up these conditions right here, these things in the parentheses, those are conditions. We can set those up specifically so that way we can go until we hit a certain point. So there's two ways that we could do this mathematically. Sure, there are probably more if you really wanted to rearrange, but it depends on what you want to feed in. So the first one, this is the one I'm going to start out using. This is the current position. So this runs while the current position is less than that delta distance right there. So we know headed in, we're going to know our delta distance because that's how far we want to travel off of our initial. I'm going to substitute in the current position. This is really going to be this because this is what we know. We're going to know our starting position because we're going to get that at first, and then we're going to know our current encoder reading, and then that's what this is going to equal. There's a second one right here. This runs while the raw encoder reading is less than the target, but then you have to figure out that target point, and that's going to be your start plus your distance that you want to travel past it. Okay. Something to keep in mind, the inequalities reflect the sign. So while I'm moving forward, this is great because it's going to run, and this thing is going to be smaller than my distance that I want to travel until I get to that point. But if I'm going backwards, this is really going to be a negative number. So so this number right here is also going to be moving backwards, this current position, because you're traveling backwards. So here, for a positive number, you're going to see like current position is less than that distance. But for a negative number, what you do is you do current position is greater than this negative distance. That's the way that you set it up for kind of forward and backwards so you can track those positions. So let's talk about the structure of this in pseudocode. So we start out, we're going to turn on our motors, and then we're going to travel, we're going to take that loop structure that we just had, and we're going to use it to go until we hit a target. And then once we're done with that, then we're going to stop. Okay? So just as a quick side note, the motors are stopped at 0% power, so you tell them to go to 0%, they should break. So we're going to go in, we're going to reset all of this fun stuff back up. We're going to go in, here we go, we're going to take the same kind of 3-step process that we've had for creating motors and moving. You start out, you create the motors, you connect them up, and then you add in your runnable stuff. So we'll start out, this is going to be a drivetrain program. So we're going to need a left motor and a right motor. Now we just get to set them up. The same thing, we're going to assign them to their relative places on the hardware map. And then we're gonna add our runnable stuff. So start out, we're missing one part of the structure here, actually. If you check this out right here, we need that wait for start. So we're going to go in and we need to add that wait for start. So this is kind of like whenever we started teleop, if you remember how we had the init and then the loop, and there was, you have that divide between whenever you press the init and then you press the play. This is the divide right here. This is that wait for start. So all right, so we're going to start out. Let's put in that pseudocode structure. So 1, we're going to turn on motors. 2, we're going to wait until target. And 3, we're going to turn off motors. Let's start out with the easy stuff really quickly. Okay. So we're going to go and we're just going to do our motors on and off. We know how to do that. That's super simple. Left dot set power. I'm just going to set this to be 40%. I'm going to copy this because I am lazy, and lazy programming is, I don't know, it works. I did that wrong. Well, lazy programming is only good if you do it right, but yeah. Okay, there we go. Okay, so we have these bits filled in now. So we have ability to turn on our motors, and then we have them off. So now we need to fill in that middle part, that middle wait. Go until you do something. So we're going to start out. First, we need to start out with our variables. So all those things, all those relations that we define, they can be defined in terms of variables. So what we're going to do is we're going to create those variables as placeholders so we don't have just a bunch of numbers floating around. Okay, we're going to start out. The first thing we're going to do is we're going to define a start position. And what that's going to be is that's just going to start out and as our current encoder position. So how you get that is you choose one of your motors, you take your left or your right. I'm going to say left in this occasion. I do dot and then I get current position. And then that gets your current encoder reading from that motor. So I'm just going to run it off the left side. You could run it off the right side. There are ways you can combine them, but right now we're just going to do single ones. Okay. The next thing we have to do is define our current spot, I guess. I'm going to call this current reading. And so what I'm going to do, I'm going to say this is also our current position because we start, so we start at the same place right here. So this theoretically, the distance between these is going to be 0 to start out with. Now we get to add in that loop structure. So we're going to go back, we're going to say while, and there's going to be stuff that happens in here. It's going to be totally cool. And then it's just going to wait, and we're going to update stuff in here. Okay. So we're going to go back to our relations. We're going to check these out really quickly. Okay, so we go back to this, and we see that we can calculate out our current position, and then we can figure out if we know this, then we'll in our starting position, then we can figure out this other target right here. So what we can do is we can take this information that we have, and we can all factor that into one of these two conditions. So I'm going to start out. I'm working off the first one. That's just personal preference. You can run over whichever one you want. So I'm going to go back here. I'm going to substitute that in. So that was the current position minus the delta. But remember, we have to substitute in. We don't know quite our current position, but we can calculate it really fast. And our current position that we found based on our relations is our current reading minus our start position. Just going to type that in really quick. So we have that, put it in parentheses just so to make sure that operation gets done. And then what we're going to do is we're going to run we're going to run while we're less than our target. So as a quick numbers thing, our Andy Mark motor encoders 1,120 ticks is a rotation. But for our Tetrix, I believe it's 1,440. So they are slightly different. Keep that in mind whenever you're coding. But that will be 360 degrees, one rotation of the wheel. Distance is determined by circumference of your wheel, and that's a little bit of trial and error, and you can work with that. So we start out. Now we have this. We're all good to go, except we need to keep updating while we're in this loop. We need to make sure that we're updating our current position so we know where we are. So what we're going to do is inside this loop, we're just going to put in an update thing. So we're just going to make that current reading. We're going to make it the newest available value that's coming from the encoder. Every time we go through this, we should be getting a new value. That's the way this is going to be set up. Okay. So that is it now. Now that we have that, so we have everything set up. See no errors. We're all good to go. Turn on our motors. You have your variables, and then you go until you hit that point, and then you're going to turn off your motors, and that is how you go forward. Now, just as quick reference, to go backwards, you're going to start your motor power going backward, and then you're going to flip these just like this. Okay, so that logic will now enable you, because of the direction that you're traveling and the way that everything's moving, that will allow you to track things backwards so you can move forward and backward based on the same thing. Okay. So let's go and talk about different kind of triggers. Let's talk about time in this example. So if we go back to that structure that we had, that we developed for moving for something, okay? So we had for moving for distance, this kind of structure right here. So we work off this, and we're going, and we say turn on motors, go until target and stop. But what if I substituted this out for something else, some other trigger? Okay. And when I say trigger, I mean we're using some other type of sensor or thing or timer or something like that we could use to track how far we've gone or whatever else. Right? So if I take this and I just substitute out this middle part, then I can kind of use it as a go until you do something and then you stop. So we can set that up based off of a few different things. So I'm going to start out with time. So time is really simple. So all you have to do for that, I'm just going to comment this bad boy out. That's how you do big chunks of code. I'm going to start out, if you put a sleep and then you input something in milliseconds, then what it does is it just holds whatever state that it's been in for this amount of time. It just sets down, and even though it says sleep, the motors aren't off, because the motors will hold the power. The way this is set up, this doesn't shut everything completely down and stop it and then resume it. It's just kind of it's like a pause but still going, if that works as an analogy. So that's how you do something based off of time, moving in autonomous. So at this point, we've learned how to move based off encoders, and we learn how to move based off time. So we know how to do those now, but what happens if I want to, when do I use each one? That's $1 million question, right? I mean, I have these two methods that I can use, and they're both great, but what are they useful for specifically? So as a quick comparison between time and distance, distance is for more precise movement, so like turning, moving to a specific tile, etc., etc. But time is a little more for larger, unprecise movements, like lining up against a wall or getting past an initial point. So like passing over a line so a sensor doesn't see it, or your robot doesn't see it, right? So the reason why this can be important is, let's say you're lining off of a wall just to kind of get centered a little bit, and you go based off distance. If your distance isn't exactly where it needs to be going up against the wall, which generally it isn't because there's always a little bit of play, your motors are just going to sit there and they're going to stall out, and if your wheels don't spin, then you're not going to be moving any distance, which means your motors are going to be pushing, 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 but they can't go, and then you're just stuck there. But with time, you can overshoot it a little bit, and yeah, your robot presses into the wall, but maybe it's only for half a second, and then it's good to go, and you know you're lined up. So just simple things like that, the strategy in using time versus distance whenever you move can be all the difference in making a successful autonomous program. There you go. That's the wrap-up. I hope you enjoyed.